side, which we are about to publish now. And this is the result. We have now a study of up to 1 year in a sheep model, and in 9 out of 10 sheep we had hyaline cartilage after 1 year, which is equivalent to a 5-year observation period in a human being. And you can see the best results on the right side, group D, and you can see a very strong layer of cartilage formed on top of the bone, and the controls on the left side, they just had a matrix on undifferentiated stem cells. Did not work so well. And the most important probably is that you see in this histology, maybe a little bit difficult to see from the back, but you can see the brown zones in group D, which is the pre-differentiated mesenchymal stem cells, and E is the normal cartilage. You can see the brown areas being a staining for collagen type 2, which is a quality criteria, and so important that it occurs over the control, which is the standard result in many clinical applications when you just inject matrix or just non-cartilage, you only get collagen type 1 formation. This is the histology. You can see the columnar formation and showing a good regeneration. So the contrast staining for the collagen type 1 is shown here in the subchondral zone on the right side, and especially the controls that were not the mesenchymal pre-differentiated cells, just in the matrix. You can see a lot of collagen type 1. So it works very well. And we hope to go into human patients now also with this third group, now with cartilage. We have done skin in a multi-center clinical trial now in Germany, and we do the bone in about 20 patients. And now the third in line will be the mesenchymal stem cell-based cartilage repair. And other applications now starting is dental and maxillofacial surgery. Other systems our group has developed is the cardiovascular approach, and one of the technology was to develop heart valves that would grow with children. Of course, mechanical valves or synthetic valves cannot do this. That exists today. It was the same concept to develop a bioreactor that should be a single-use device with the duct allowed to inject only stem cells. A microcontroller should run the process, and we in our labs, offices would just sit on a web-based interface and see what's going on. That this is reality now happening. We have done in cooperation with a Polish group in such a sheep implantation with the intraoperative process now with Dr. Wilczek. And I will show you some experimental developments. Of course, we have not reached the maturity like we have it in bone and cartilage, but the concept is very similar. Unfortunately, the video is not running. Now it's starting. You can see the scaffold, the carrier matrix inside the material that will eventually be copied and remodeled. It's inserted, the bioreactor is made like a trolley. You open and close it, we put in the materials, check the stem cells, and then it would start to rotate to allow the sedimentation of the cells. Now the remodeling of the matrix is shown here, so the recipient's cells which are integrated, remodel the matrix starting in vitro and making, for example, human procollagen. You can see here the formation in the bioreactors. Also, these bioreactors have a mechanical stimulation inside, and we have implanted sheep a few years ago already, and now about 10 children have been treated with this previous technique, but now the most advanced will be the intraoperative processes. You can see. This is a heart valve on the left side. After 4 weeks, and you can see a strong integration of the cells. The controls that were non-seeded always had a scar-like appearance. And you must remember that also in the child that I showed you before, we had a scar-free healing of the skin, which is probably one of the most important achievements that we have done in burns, that you can really activate the stem cells to go into real healing, scar-free healing, and which may be mimicking what's being seen in this heart valve. Now, control, this is already an intraoperative prepared vascular structure. This for coronary heart patients, a vessel that had a diameter less than 5 millimeters. It took 30 minutes repaired. We coated them with stem cell, was implanted in an arteriovenous shunt situation, and was removed after 4 weeks on sheep body. You can see a very nice and shiny wound inside. It is only a polyester-based graft that has a high thrombogenicity. If you had no stem cells, it always clotted, as you can see in this control. So inside the patient, the human being is a bioreactor. The bioreactor human being completes our work and makes the tissue, finally, as you can see in this histology. Now, fourth field is neural regeneration. We developed also bioreactors to automate the preparation of these cells. And you can see the stem cells here moving And when I was in school many years ago, my teachers told me the brain can regenerate. You can see here it's not true. And when we add vitamin C, they will start to make neuronal extensions. And we are now trying to get approval from Apple to treat patients with spinal cord injuries, and we hope to do this in October, because the same process that we have done bone cartilage or the skin can be applied to topically repairing the injured spinal cord and inducing the cells to regenerate on site. Now, some earlier work also shows that during oxygen deficiency, which you can see the cells try to extend much better, they propagate much better than in normal room ambient oxygen, and even for making photosynthesis positive cells like a bottom, which is important for Parkinson therapy. Now, my last field, which we had a cooperation with Professor Cherinkova in Prague, we developed an animal model, and she did the operation liver resection. You can see P67 staining on the top in a laparotomy situation, and in the bottom 7% partial appendectomy, the liver goes into regeneration as a mitosis, but the same molecules that we used in the burn patients enhance liver regeneration quantitatively, but there's no qualitative change. But the most important finding probably is the controls that you see on top right, that nothing happens if there's no trauma. And you may remember the other talks speaking about inflammation. What we have probably found is a mechanism to use inflammation, activate stem cells, lead the stem cell through a window of repair, which is finally resulting in a self-terminating process, because if there's repair and regeneration occurring, the inflammation stops. That's what we have shown also clinically. And it's probably due to, same like in the skin, due to endogenous stem cell activation, which you see at the bottom, CD90 positive cells popping up in the liver tissue, only in the trauma group, which has been treated. Normally they would be located just around the vascular structure. In the theory about how liver regeneration occurs, first the hepatocytes would go in repair, and then the stem cells may come, and we may have found the mechanisms to activate them. Other extracorporeal systems that we have developed in the past, as shown here with the animal model, the increase in brain pressure is typically in the full hepatectomy, the barrier prolonged survival, but one of the limitations the reason has not gone to clinical applications so far is the shortage of human liver cells that we can grow in vitro. It's only so far animal-based, and we hope to work more on stem cells in the future. But at least it's a barrier that can be cryostored, so the idea was to, when we succeed with this last project, also to expand cells, store them, cryopreserve, and then use it like a blood bank. Now, why would we use these bioreactors? I think these are instruments for mass production, in the sense that you have now finally a tool to make stem cell therapy available for everyone at a relatively low cost, extreme short periods of time at the world's highest standard, because it's a fully closed environment and fully controllable and fully sterile. And so the bioreactors are prepared by integrating the biomaterials, the scaffolds, the materials that will eventually be copied to be remodeled into the patient's own recipient tissue, like the target tissues, and their instruments to position cells to achieve mechanism and structure. And I spoke about it only very, very briefly. So the bioreactors making cartilage have magnets inside, the stimulator cells. The hardware of bioreactors induce distension. And it's also an automation and standardization process. So what we do, in this concept, there's not a product in a sense they would make a piece of skin or a piece of liver or a piece of hardware. It is only a process, and the patient's cells would be the only variable in this process that would be eventually done in any clinical environment. And now, the stage where we are right now, we are in a production phase of the sterile equipment, which are the bioreactors, and doing compassionate use cases in some multi-center clinical studies now with burns and bone is starting, and parallel we are applying for a GMP process approval, which is a production license that we will do, and I think in some cases, I hope we have a routine therapy strategy in 1 to 2 years for this. Now this is the acknowledgement of our research team. There's a lot of doctoral students, PhDs, and postdocs and technicians from our team. So I thank you very much for your attention.
Thank you so much.